Hello everyone, this is Brian, recording another video lecture for CSC 143. In today's video, we're going to be covering Big O, a means of measuring performance, and the ArrayList data structure, which we've seen in the past, but perhaps we haven't quite fully understood. Before we dive into how we measure performance, I want to present this in the context of the ArrayList. The ArrayList is a generic Java class that holds a list of objects. We've seen the ArrayList already in previous examples. We've imagined the ArrayList as like an array, but automatically expanding in size when the array needs room to grow. For read and write operations, the ArrayList class is going to match that of primitive arrays. The equivalent of the ArrayList method call to the primitive array operation is shown in this table below. For item assignment, we can perform the same thing using the set method for a particular index. For item retrieval, we can do the same thing using the get method. And to determine the length of the array, we can use the size method on the ArrayList. So, on the surface level, it may seem like the ArrayList is merely a wrapper around the primitive array, but it's got some interesting features that I'd like to talk about now that have certain performance implications upon using the ArrayList versus the primitive array. So in Java, arrays are actually a fixed length. If I declare this array of integers called num, using the new keyword here, I have to specify an integer constant that represents the maximum amount of values that I can store within this array. Now practically, there's no such thing as an unlimited length array. What I mean by that is there's always going to be some bound to the amount of memory you have in your system, and you can't also say int bracket infinity. There's no way to specify that in Java. If you attempt to make an access outside the array, an index that's beyond the length, or something negative, you'll get an array index out of bounds exception. Let's take a look at that in action in the first arrays test. Let's go ahead and run it to make sure it all still works. Great. On line 17, I declare a new integer array. I use the length property to look up the length of the array, the number of values inside. Then I go ahead and do some assignments. The first three numbers, 0, 4, and 9. Next down here, I actually overwrite those numbers with just the numbers from 0 to 4. Then I can assert that those are the numbers I pull out when I use this bracket notation to look up the values within the array. Then finally down here on line 33, I attempt to look up index 99, which of course is beyond the number of elements inside the array and is not a valid index for this particular array. Normally, if I successfully completed this statement, I would reach this fail statement and the test would fail. But what Java is going to do is between lines 33 and 34, it's going to throw an array index out of bounds exception. It'll reach this catch block, the catch block will run, and bypass the fail statement. This is the same pattern you've seen in your project assignments, where the expectation is that an exception gets thrown, and that's going to bypass the fail statement, which would be hit if the exception is not thrown. So primitive arrays should be pretty familiar to you. The syntax is largely the same for just about any programming language. You can recognize the bracket notation in a lot of places. In Java though, Java is not going to let you have unlimited length arrays. We must declare the length of the array at the definition of the array, which is not the same as with some other languages. Like with Python and JavaScript, you can essentially get unlimited length arrays for free just via the array construction. But here in Java and C and some other languages, we're going to expect arrays that have a fixed length. The length limitation for arrays is because of how arrays and objects are stored in memory. By definition, an array must take up a contiguous chunk of space. Writing beyond an array is dangerous because it can and will overwrite other objects that are stored coincidentally nearby. Let's take a look at the whiteboard to see how arrays are stored in memory. Let's suppose for a moment that we declared an integer array with 4 numbers inside. In Java, arrays are fixed length, and by nature, all the data is going to be stored contiguously. Since these are just plain integers, these primitive integers, we know that they're stored value-wise. So that data is just going to be stored back-to-back contiguously. The first number, 4 bytes, is going to be stored in the first index at the very beginning of where the underlying memory address of the array points to. Then the next 4 bytes will be stored right after that, and so forth until we reach the end of the array. If we attempt to read or write outside of the boundaries of the array using an index that's invalid, Java's going to stop us from doing that. A significant advantage to using primitive arrays is very fast lookup. To compute the memory address of a particular index within the array, all Java has to do is figure out what the underlying memory address of the array is, and then multiply the index we're looking for by the size of the items being stored. So for example, if we know the item width is 4 bytes, integers are 4 bytes, and we're trying to get to index 3, I can do 3 times 4, the index multiplied by the width, to get an offset of 12. And I add 12 to whatever the original memory address I had was, to reach the location of the third index. If these were reference types we were storing inside this array instead, reference types as in object types, classes that you define, these of course would be references instead, and these references would go about pointing to their own true location in memory. With that in mind, how is it possible that the array list can extend its length? If we have fixed length arrays that have to be limited in size, defined in construction time, how can ArrayList give us this abstract version of an array that somehow automatically knows how wide our array needs to be? Let's go back to arrays test and see how that works. On line 41, I declare a new array list of integers called numbers. I assert that it's currently empty, there's nothing inside. Check out this constructor here. I don't have to declare a fixed length, and the size actually starts at 0, unlike with the array constructor, where I had to declare that fixed length and the length was always defaulted to that length. Then down here, I go ahead and add the numbers 0 to 4 using the add method for ArrayList, and I see that the size of the ArrayList has grown up to 5. I can retrieve individual values outside of the ArrayList by using the get method, and then I can continue adding numbers to the end of the ArrayList just by calling the .add method. One way we can get the last value within the ArrayList is to use the size method, which returns the number of values inside the array, minus 1, to get the very last index of the array. We have to do that minus 1 because of course arrays are 0 indexed. Indexing starts at 0, so the last element, the last index inside the array, is going to be the size minus 1. Even with this additional flexibility, ArrayList won't let you assign arbitrary indices. You would still have to manually append items until you reach the index you want. For example, here I'm trying to assign at index 123 the value 321. That is going to throw an index out of bounds exception because the size of the array list is not yet 123, so I'm unable to assign a value there. So how does this work? How is it that ArrayList can somehow know in advance how many items I want to put inside the array without me having to define in advance how wide I want the ArrayList to be? The ArrayList is indeed backed by a primitive array, but we're going to abstract away the fixed length limitation of arrays so that the ArrayList itself provides this notion of unlimited length. The procedure is actually quite simple. We initialize the array with a default length. When the array expands beyond the length, we're going to allocate space for an array that's twice as long, then copy object references over to the new array. That new array becomes the underlying array inside the array list. Then we repeat that process moving forwards. We fill up the array, when we run out of space, we copy all those items into a new array. This is going to give us the illusion of an unlimited length array because I can continue to append items to it, and as soon as I finish that method call, then all those complex copy array operations are going to be done inside the array list. Let's see how that behaves in memory by going back to the whiteboard. Okay, let's suppose I declare an array list of generic types, L, and that array list starts with 3 values to begin with. Then, I keep appending values after I've made all those 3 values already. Once I run out of space, what the ArrayList is going to do underneath is it's going to go find a space that's twice as long. It's going to then go copy all the elements that I've already stored inside the array into the same respective indices inside the new array, and that new array that's twice as long is going to become the underlying array for the ArrayList. This gives us the illusion of unlimited length. It's a dynamic length array. The data is still backed by a primitive array, and we still get fast lookup operations because, again, lookup is just a matter of computing the offset from the original location of the array, but we can continue appending items without ever running out of room. Let's go take a look at the ArrayList constructor, from the official Java docs. Remember, whenever you look up documentation online, make sure to append 11 or whatever specific Java version you're using, so you go find the accurate APIs. Then go and open up the official Oracle docs. Here we see class ArrayList is part of java.util and java.base, so I can import the ArrayList via java.util.ArrayList. If I scroll down, I see a description of how the ArrayList behaves. I'm told that each ArrayList instance has a capacity. The capacity is the size of the array used to store the elements in the list. It is always at least as large as the list size. As elements are added to an ArrayList, its capacity grows automatically. The details of the growth policy are not specified beyond the fact that adding an element has constant amortized time cost. This is really a fancy way of saying, on average, adding elements to the array is just as fast, regardless of whether or not it has to do an expansion. How does that work? Well, most of the time, there's going to be room inside the array. So I add items, I move on. I add items, I move on. It all happens very quickly, just as fast with the primitive array. But then, maybe one every out of n additions, I have to do an expansion and double the amount of space inside the array. You can start to imagine that the copy operation, the allocation and the copying, is going to take time. There is indeed a computation cost to that, and we'll talk about it in a second. But the fact that we really only have to do it once every n write operations means that overall, the speed of which we append things is about the same as with just a fixed length array. If we scroll down and take a look at the ArrayList constructor, we see that the base ArrayList constructor constructs an empty list with an initial capacity of 10. We can specify an initial capacity by hand by passing it into the argument. And there's also a third constructor here that accepts a type of collection, such that it's going to construct a list containing the elements of the specified collection, in the order they are returned by the collection's iterator. This constructor can be used to essentially convert a collection, which can be one of several types, like a set, or a list, or a tree, and turn it into an array list. This is going to be done by walking the elements within the collection using the collection's iterator, just as we would iterate over any other iterable data structure. Now we've learned how array indexing is fast, because it's just a matter of computing an array offset and adding that to the base value memory address of the underlying array. But extending, as you can probably imagine, is quite slow. We had this whole big discussion about why references exist. That copying values, Java's pass by value, arguments and return types are copied, copying values is computationally expensive. And it definitely doesn't scale up with the size of our objects, in the sense that our program's going to slow down as our objects get bigger and bigger. So instead, what Java's going to do is it's going to keep track of references to all the objects it's managing and copy those references around instead, where each reference is really just a pointer underneath that's about 4 or 8 bytes wide. So with that in mind, how do we measure the computation cost of these kinds of operations? How can we say in a technical fashion that this copy operation is explicitly slower than just this write operation? And that's where Big O comes in. Big O is a mathematical notation that describes the runtime or space of an algorithm, function, or procedure. Formally speaking, Big O is an upper bound of the growth rate of a function. We can compute Big O with some simple rules. Number 1, start with an input or backing data structure of length n. Number 2, count the number of steps in the algorithm as a function of n. And number 3, drop constants and constant multipliers. Let's walk through several examples in BigO.java. Let's start out at the top. I initialize an array of a length n, and then I try to retrieve values outside of the array. You may think that, wait a minute, the act of allocating space for n items, that certainly takes time too. We'll talk about that in a little bit. For now, let's just say that we have this array and it has a length n inside. Retrieving items outside the array, we said that was fast. Well, how fast? It's constant time fast. That is going to be O of 1. Even if we have an array of length n, retrieving any index within the array is always going to be 1. Why does that make sense? Well, we talked about how we're always going to multiply the width of the elements times the index to get the underlying memory address. And one step of multiplication is very easy. It's very fast for the computer to do. And that is not going to get more complicated as the size of the array grows. It's still one mathematical operation. So, regardless of what literal computation time it takes, 500 milliseconds, 500 nanoseconds, we drop constants and constant multipliers. This can be kind of thought of as 500 times 1, so really we say it's O of 1. The same thing goes for the set operation. Assigning a value in memory is also O of 1. Assigning a value inside an n-length array is not going to be affected by the amount of items inside the array. This is because array lookup is fast, it's just a matter of multiplying to find an offset, so we can do it in O of 1 time, not a function of the length of the array. What about property lookup? Doing something like array.length. This too is going to be constant time. It's constant time because Java is going to go figure out where the length property lives on the array reference. And this is going to apply to all arrays. So really, whenever you do a property lookup on any type of objects, the actual act of looking up that property is O of 1, because that property itself will exist at some fixed offset from the location of the item. Okay, so those are all pretty quick operations. What about this one? Here I've written a method called indexOf. The indexOf method is going to go return the index of the underlying object I'm trying to find within the array. If that index does not exist, because the item does not exist, I'll return -1. This implementation is fairly simple. I write a for loop. I'll start out with index 0 all the way up to the length of the array. And then I'll retrieve items outside of the array using that get method I wrote above. If I just so happen to find the integer that I'm looking for, I'll return the index in which I found it. Otherwise, I'll return -1. Okay, let's go through the 3 steps. We have an array of length n. At most, when we reach line 32, we will have walked every element inside the array. So as a function of n, we have to do n steps to get to the very end of the array and find the element we're looking for. N steps for an n-sized data structure We call that O of n, linear time. It's linear in the sense that we have to individually examine every element at least once. It's not multiplicative. We don't have to do it n times or n squared times, so it doesn't grow in that fashion. It only grows as some factor, constant factor, of the length of the array. I do want to make this point clear on dropping constant and constant multipliers. Let's suppose for a moment that I was writing a function that looked like this, where I had 2 of n lookups. I have to watch each element twice. Well, 2n, drop constant and constant multipliers, I drop that 2 in front, and I get O of n. So what's interesting about this is even if you have a constant in front of the computation for Big O, we're going to drop it anyway and bring it down to a general class of Big O. This one happens to be called linear time. Let's go a little bit further. What about this definition of public string toString on line 37? Well, it's only got one line, so does that mean it's an O of 1 constant time function? Unfortunately, no. The number of lines in the program is not necessarily correlated with the actual runtime performance of the program. And it's important that you realize, even when it looks like there are some pretty simple looking function calls inside, they may amount to something that is more than just constant time. Boolean operations, integer operations, mathematical operations, those are usually constant time. But method calls, well, those abstract away underlying behavior and complexity. Those themselves can have computation cost of their own. This call to arrays.toString, let's talk about this. Arrays is a helper class that contains many helpful methods for manipulating arrays. The toString method is a static method on arrays that converts an array into a string representation of comma-separated values. So it'll take whatever numbers are inside this array and output a string that includes those numbers separated by commas. If you're curious of how it works, you can actually control-click on the arrays.toString definition and take a look inside. Essentially what it's doing is it's constructing a string that starts with a left bracket, appending items, separating them by a comma, and finally ending with a right bracket. So you can sort of imagine how an array would look like in text form. In any case, even if we don't know how the underlying behavior of toString works, we can infer, based on the output, the runtime cost of actually calling it. If I know I'm going to have to walk through every element of the array to convert each of those elements to a string, but I only have to do it once, we can infer that the Java engineers did a pretty good job, and at least they had to walk all elements once, and they wouldn't have to do it more than once. So I'd say, based on that argument, arrays.toString is going to be linear time. It would be kind of silly to make it something worse than linear time. That would involve walking each element more than once, which doesn't seem at all necessary for a toString function. With that in mind, arrays.toString being linear time, O of n, we say the overall function itself is O of n. Again, don't get confused with the concept of line number count and actual performance cost. Line number count can sometimes serve as a hint towards what's going on, but it will also abstract away the underlying cost of the individual method calls that are being made. Let's keep going. Check out this function called triangle, which returns a character array of characters. This is actually a character matrix. It's a two-dimensional array. And we're starting with an array of characters, and it gives us an array of characters. That's one way you can read this notation. So I can build this two-dimensional array matrix by using the same notation as I would with the definition. I can declare the number of rows inside the matrix, and then the number of columns, the amount of elements within each row. Now check out this inner body of the for loop. I traverse each row all the way up to the length of the square, which is n, so that's at least O of n. And then I traverse each column up to the row number I'm currently at. So if I'm at row 1, I only go up to row 1. If I'm at row 2, I go up to row 2 and so forth. You can imagine this in your head as drawing a triangle, a 90-degree triangle with the 90-degree point on the lower left, because as I go down each row, the column width goes wider and wider. Does that mean that this is going to be n squared over 2? Well, this operation, this right operation, is O of 1. Walking up to the end of the row, that's up to O of n when row is equal to n. And this loop out here is going to be O of n every time, because we're going to the end of the length of the square. So with that in mind, O of n times O of n gives us n squared. You could argue that, well, hey, if we're building a triangle, we're not actually having to traverse every single element inside n squared, we're really only traversing n squared over 2. But remember, step 3 tells us, drop constants and constant multipliers. 1/2 is indeed a constant multiplier. So what we actually get here is still O of n squared, which we consider quadratic. This pattern does scale up. Here is an array of integers, an array of an array of integers, an array of an array of an array of integers, so a 3-dimensional matrix. If we want to place numbers inside this 3-dimensional matrix with 3 nested for loops, the multiplication applies just as before. We have an O of 1 operation that's inside. We have a loop that wraps that O of 1 operation n times, so that gives us n times 1. We have a loop that wraps that n operation, so n times 1, which gets us n squared. And then we have yet another loop on the furthest most point that gives us n times n squared on the inside, giving us a total of n cubed performance. As this exponent gets bigger and bigger, the greater this runtime cost is going to scale up as n grows. For a lot of algorithms, n squared probably isn't that good. You can imagine n squared grows pretty quickly. For just n of 1,000, n squared gives us 1,000,000. For n cubed, n of 1,000 gives us 1,000 times 1,000, which is 1,000,000, times 1,000, which is 1,000,000,000. So computing a cube that is 1,000 width, depth, and height requires 1,000,000,000 operations. And suddenly, it's not going to scale up so well, no matter how fast of a computer we get. The faster computers we get don't scale up like this. They don't scale up exponentially. They don't scale up quadratically. Instead, computers are just going to get faster and faster in terms of the amount of instructions they can perform per second, floating point operations they can perform per second. However, that sort of linear growth is not capable of accounting for the speed at which n and big O of n can grow. This is very much something that we explored on the first day, when we wrote that very simple looking Fibonacci function, and we told ourselves, well, this might be the right implementation, by nature of Fibonacci the sequence being defined this way, only for us to discover that this would actually take millions and millions of years to finish computing, even on a relatively fast modern desktop computer. This is because sometimes the big O performance of the algorithm can scale faster than our computers can throw at it. Even though our n may seem innocent and small and grew up to be relatively small, it's this computation cost that really kills and can slow down performance of our algorithm. Let's keep going and take a look at some other different examples. Here's a function called selection sort. Selection sort is one of the few sorting algorithms we'll be learning inside this class. And selection sort is one of those naive algorithms that's going to do the simple thing and just try and go out and select the minimum value and place it at the very front of the array. In order to sort items, there's a lot of ways and strategies we can actually do sorts. Selection sort is one that you might come up with if you ask a child, or you just kind of do it on your own with maybe a deck of cards. And it's one of my favorite algorithms because of how simple it is to implement. We need to maintain an unsorted partition and a sorted partition, where the unsorted partition starts as the entire array and the sorted partition starts as empty. Then over time, what we're going to do is walk the entire array to go find the minimum value. As soon as we find that minimum value, we'll go move it into the sorted partition. We'll do this over and over and over again until we finally made the sorted partition equal to that of the unsorted partition. Well, what was previously the unsorted partition, which is the entire array. Let's take a look at how that behaves in terms of Big O. Writing a function to find the minimum element within an unsorted array is always going to be O of n. That can't be avoided. We do have to look at every single element to go figure out what is the smallest one. Then, doing that for every single element, that is, finding the smallest element n times, is going to be n times n. That gives us a sorting algorithm that's n squared. Again, n squared still isn't really good for a lot of algorithms. The optimal sorting algorithms are actually n log n times the logarithm base 2 of n, which actually grows much slower than n squared. However, one great advantage to this selection sort implementation is just how simple it is to implement. If I asked you to implement selection sort on your own, I imagine that you could do it with relative ease. Writing the min function isn't so hard. You just have to keep track of the last known minimum value and replace it as necessary. Then writing the swap function is just 3 lines to exchange this newly found minimum with its new location on the sorted partition. So one of the trade-offs that we have to think about when writing algorithms in this class is not just the raw runtime performance, but also the burden it places on us as developers to engineer and maintain that kind of solution. If it's very mentally complex for us to understand a more optimal sort, or maybe we have more time and faster processors and smaller datasets, it may make more sense to just have algorithms that are slightly less efficient for the sake of our sanity and better maintenance. On the flip side, if we have weak processors, we have large datasets, and we have a good grasp of what we're doing, then maybe we should opt for one of those more complex algorithms, like merge sort or quick sort, that can scale up much better as n grows. How about this function here on line 93? Public boolean is sorted. As you can imagine, this is going to return a true or false value that indicates whether or not the array is currently sorted. One way we can do that is start out with the first value of the array, then walk every other value of the array. And if there's any circumstance where we find a value that is not greater than the existing value we're looking at, then we know that it's not sorted in ascending order. Otherwise, we'll just move our current value forwards and keep looking forwards. So another way of thinking about this is we look at each element and we expect the next element that comes after it to be greater than itself or equal to. If that's the case, and we pass all those checks, we can return true. Otherwise, we'll return false here. I think this one's pretty easy. We only have one for loop. It's even a for each loop, so it's going to perform iteration for every element inside the array, which is of course O of n. And each of these operations is O of 1. With that in mind, this is going to be a linear function. In contrast, the actual act of sorting was a quadratic function. What I want to demonstrate to you here is how the act of solving the problem, that is actually performing the sort, and the act of validating the solution, checking to see if the list is indeed sorted correctly, those two implementations will have different runtime costs. It is easier to determine if the list is sorted than the actual act of doing the sorting. It's actually a pretty large problem in computer science, and a question that a lot of researchers are working on, of whether or not we can come up with a solution to any computational problem that's as fast as the solution for validating a solution to that problem. The big question is there such thing as a sorting algorithm that's linear time, that's just as good as this is sorted method here? There's a set of problems in the world that we haven't quite solved yet to this degree, and it's something that a lot of researchers are really focused on because it can have certain implications on real-world applications, such as cryptography, where we want it to be hard to come up with cryptographic keys, but we want it to be easy to validate the correctness of those keys. let's look at something that is a logarithmic function called binary search. You may have heard of binary search before. The idea of binary search is given a sorted list, we can find an element in the list efficiently by starting at the middle, asking ourselves whether or not we are targeting a value that is less than or greater than the value we're currently at, and then navigating to the partition of the list that contains the value, with the knowledge that the list itself is already sorted. Let's take a look at my binary search implementation. If I'm looking for a particular target, and I'm doing it within the partition of begin index and end index, if I ever have a scenario where the partition is invalid, I know the element is not inside my array. If I am in a case where the partition only contains one element, then I may have found the element, otherwise I have not. And then this third case where I've found an element, but it's not quite the element I'm looking for, I either want to look above on the upper half of the partition or below on the lower half of the partition. If this list is sorted in ascending order and the element I'm looking for, the target, is greater than the element I'm currently at, then I should go look at all the elements that come after that current element. Correspondingly, if the element I'm looking for, the target, is less than the middle element, the element that I'm currently sitting on, then I should go look at all the elements to the left that are smaller than that middle element. The smart thing about binary search is that it efficiently cuts the search space in half with every step. If I start with an n-length array, and I don't find my element on the first try, then the remaining search space is going to be n over 2, because I'm going to know that my element must either exist in the half partition that remains, or not exist at all. This is going to behave recursively. With every call to bin search, I'm, once again, examining the middle element, and then partitioning the remainder of my search space to be exactly half of what it was before, so that I'll eventually narrow down those halves until I find the spot where the element I'm looking for belongs, or I won't find it at all. The clever thing about binary search is that it scales up extremely well. By nature of cutting the elements I have to look through in half with every step, I can actually apply binary search on lists that are extremely large with great efficiency. The actual runtime cost of this would be log of n, log base 2 of n. A logarithm can be thought of as the inverse of an exponent. In this case, with log base 2 of n, log base 2 of n is equal to the value that x would have to be if 2 to the x equals n. So one way of thinking about this is, well, 2 to the x grows extremely quickly. It doubles with every increase of x. And the outcome is that we get bigger and bigger n. Correspondingly, as n grows, x grows much slower. Well, what do I mean by that? Let's say 2 to the 10 is 1024. That's an easy number to remember. Or it's a good number to memorize because it's roughly 1,000. 2 to the 20 is 2 to the 10 times 2 to the 10, which gives us 1,000,000, 1,000 times 1,000. But the difference between 1,000 and 1,000,000 is quite a lot, whereas the difference between 10 and 20 is quite little. So while exponents will grow extremely quickly, logarithms will not. Logarithms are the inverse of exponents. So here, as n grows, the actual logarithm of n is not going to grow nearly as quickly. If n was 1,024, log base 2 of n would be just 10, because 1024 is equal to 2 to the 10. If n was 1,000,000, log base 2 of n would just be 20, because 2 to the 20 is roughly 1,000,000. So the crazy thing about logarithms is that they are so efficient in how they can tackle these large numerical values and shrink them to something that's actually computationally feasible. Suppose for a moment that I had a sorted array that had 1 billion items inside. That's 1,000 times 1,000 times 1,000. That's roughly equal to 2 to the 10 times 2 to the 10 times 2 to the 10, which, putting those numbers together, gets you 2 to the 30. That tells us that the logarithm, base 2, of 1 billion is just equal to 30. So I can walk 1 billion items and find the element I'm looking for in just 30 steps by cutting 1 billion in half, cutting that half in half, cutting that half in half, and so forth until I've narrowed down my solution space to just one element. This is kind of the miracle of binary search, and we're going to see binary search later on in this course as well. But I do want you to really appreciate this log base 2 number, and how it's so much better than these other examples like n squared or n cubed, whereas n grows, the runtime is going to grow much faster than we can keep up with. And of course, our old friend Fibonacci. This one calls the function fib recursively twice with every call. If we're trying to get the number n, then we have to go double the number of function calls with every single step on the way down the ladder of Fibonacci. That gets us 2 to the n exponential. In fact, this is the opposite of what we got with binary search. As n grows, the amount of computation steps we have to do grows exponentially. Whereas with binary search, as n grows, the amount of computation costs we had to do grew logarithmically, which was much slower. Down here, I have a main method that you can run in your own time to play around with some of these methods. One of the things it does is validates that my sorting algorithm works correctly. Whenever I write these algorithms, I'm always worried that they don't work and that I've forgotten everything I've learned in school, but fortunately it does seem to work, so there's that. My binary search seems to work as well, and here's my neat little triangle. So the result of doing the drop constants and constant multiplier step is that we get several common classes of Big O that we can group algorithms into. From fastest, most efficient, to slowest, least efficient, we saw, number 1 in first place, constant time. This function does not scale based on the input size. Virtually instant. Array lookup and assignment are both constant time. No matter how big the array, we can always go get the index that we're looking for in exactly one step, just by doing that offset calculation. Next after constant time was logarithmic, which is a function that scales based on the log base 2 of the input size. As the inverse of exponential, it's going to grow very slowly. Where exponents grow extremely fast, the logarithm is going to grow much slower in order to keep up. The poster child for logarithmic functions is binary search. It's going to have the input space, the search space that it needs to walk through every single step of the way, such that we can process extremely large quantities of data in a very digestible number of steps. Next in line was O of n, linear time. This function encounters roughly element inside the input. This is generally pretty quick because we have relatively fast computers now, but logarithm is much preferred when available because again, logarithm grows much slower. Logarithm of a billion is only 30, whereas a billion is still a billion operations for O of n. N times log of n, or n log n, sometimes called linear arithmetic, is one that we haven't seen before, but it's one that we'll see soon. This is actually the runtime cost of optimal sorting algorithms like merge sort and quicksort. Linear arithmetic, n log n, is worse than linear time, but not by a significant amount. Optimal sorting algorithms are going to be linear arithmetic. What do I mean by not by a significant amount? Well, we just learned how log of n doesn't really grow that fast. O of n grows quite a bit faster than log of n. So even if we had a billion, 1 billion on the left here, multiplied by 30 on the right here, isn't that much worse, I suppose. It's much better than quadratic, which is the next one we saw. If we had a billion times a billion, well, that is some very, very large number. We would much rather have 30 billion than a billion times a billion. Quadratic is going to grow quickly, really only well suited for small n. Smaller sorting algorithms, or slower sorting algorithms, like selection sort or insertion sort, are going to be quadratic. This is almost always the case when you see two nested for loops. Even in that triangle example where we had n squared over 2, it still boils down to n squared performance. And remember, we're going to do that drop constant and constant multiplier step, so we'll bucket that algorithm inside the same category. Some really slow ones here. O2 to the n, exponential, grows extremely quickly, intractable for large n. There's some circumstances where this is necessary, like a flood fill search algorithm for a binary tree, and that native Fibonacci recursive algorithm. Of course, naive Fibonacci recursive algorithm. Of course, if we can find a solution that's better, like that iterative solution Fibonacci, we'd like to use that. But there are some natural circumstances where we do need exponential steps to process a structure of size n. One way to think about one actual application of this is an exhaustive search of a binary tree. If I have a binary tree that is a tree such that each node has 2 children, we'll learn about trees in a couple of weeks. To search a tree of depth n would require 2 to the n examinations of nodes, because with every node, I have to go look at 2 of its children and so forth. This is pretty much identical to native Fibonacci. We can think of each call to Fibonacci as being the base of a tree, such that that tree's base value is going to be the sum of its 2 children, which I then have to go figure out the sum of those 2 children, or 4 children, and so forth, growing exponentially. Factorial is perhaps the fastest growing of the bunch, n times n minus 1 times n minus 2 all the way down. This one grows intractably large and fast. There are some circumstances where this is useful, like computing all the permutations, shuffles of a list is n factorial, because there's n factorial combinations. One way of thinking about this is if you want to figure out all the combinations of a deck of cards, you can pick each card, then pick one of all the remaining cards, well, of which there are n minus 1, and then for the next card, pick one of all the remaining cards, which is n minus 2, and so forth until you've picked all the cards. And then you have to cycle through all the remaining cards. There's going to be a lot of permutations available. That would be n factorial. Now, Big O analysis is quite common during technical interviews, and is something that you should always be conscious of while programming. Oftentimes, programming challenges are designed to test the efficiency of your algorithm alongside the correctness of your solution. What I mean by that is, you might see some challenges on LeetCode or HackerRank, where it may be easy to pass the first couple of test cases with a naive solution, like that naive Fibonacci, but then you'll run into these more advanced cases where you have input sizes that are much, much bigger and really only scale well with efficient algorithms. So now that you're empowered with the knowledge of Big O, it's important that you are also conscious of the algorithms that you're writing and how they're going to respond to larger and larger datasets. For small n, any algorithm is okay. If you have an n that's really not that big, even something like 20 for exponential, there's really only a million things. Computers are fast, we can deal with it, we can handle it for now. Sometimes you want to make trade-offs based on simplicity and efficiency. If you're writing a small application and you don't want to spend too much time on it, and you know your datasets are within reasonable size, then maybe don't worry yourself too much about hyper-efficiency, and just get the job done first. As a remark, log of n, which I've hyped up about a lot, and O of 1 are actually quite close in practice. I've talked about how log of a billion, 2 to the 30, is really just 30. So when there's opportunities to get log of n, we really want to take advantage of those opportunities. And log of n's capacity to suppress large numbers is almost as good as O of 1's constant time, simple, ultra-fast performance. So with that in mind, we should strive to reach something like log of n with all the things that we write. And we're going to end up seeing binary search as a recurring theme throughout this class because it's just so good. Now that we know how to do Big O analysis, let's do an analysis on arrays and array lists. Indexing, as we talked about, is always going to be constant time. This operation is going to be fast for contiguous regions of memory, because to find an offset, all we have to do is compute the offset amount, or the index amount, multiply that by the size or width of the elements inside, and add that to the very beginning address of the array. Searching is a bit more complicated. If we have to walk the entire list for some reason to go find an element that we're looking for, maybe we're trying to look for the minimum element inside the list, that's going to be O of n. If we have a sorted list though, that gives us some great advantages. We can look through the list and find an element within log of n time, which is going to scale up much better than O of n. When it comes to sorting, the optimal performance algorithms for sorting a list are actually going to be n log n in the best case, like merge sort and quick sort that we'll learn about in a couple of weeks. That's not so bad all things considered, though there still is this n multiplier in the front. For the naive algorithms like selection sort and insertion sort, these are going to be n squared, which isn't quite as good. In fact, it's quite a bit worse than n log n, but you are going to find that these naive algorithms are a lot simpler to implement. In older programming languages, like C, finding the length of an array was actually kind of hard, because it wasn't something that was tracked inside the data structure. But fortunately in Java, thanks to an internal length property, we can quickly determine the length of an array in just O of 1 time. In general, property lookup is a form of indexing. The length property is always going to be stored at a predictable location and offset from the base memory address of an array. So for all arrays in Java, all Java has to do is jump to the offset of where the length property is stored and read that value. Now let's talk about the size of the array itself. In memory, well, if we have n elements, we say it's going to be O of n in terms of memory cost. We can use Big O not only just to evaluate runtime, but to evaluate the amount of memory consumed by a data structure. Overall, arrays are quite efficient. But frequently we need to do things more than what the humble array provides. The array itself is fixed length. The ArrayList gives us some methods that are going to abstract away that length limitation. Recall that the ArrayList is going to double its internal size anytime it's completely full. For this append back operation, the add method, on average is going to be O of 1 because we don't have to do any extending. But on occasion, when we fill up the array, we do have to copy all the elements over, which require reading all the elements inside the array, a linear time operation. If you remember in the Java documentation, it said that on average, we're still going to get O of 1 performance. And it's this idea that if we have an n-sized array backing the array list, we have to add n items first to fill it up. Then once we finish adding n items, because we're going to double the amount of space left, for that only that n plus 1th call for appending to the back, we have to double the size and copy all those elements over. So if on average for every n operations we only have to do it once, then arguably O of n divided by n, where that O of n in the front is going to be the copy operation cost, and the n in the denominator is the individual add operations that we're performing on the array list, that gives us something that resembles O of 1 performance. A sort of unfortunate consequence of this is that the array list performance itself can be kind of unpredictable. Remember that most of the time, yes, you're going to get very fast performance. But when you're building up an array list from a very small amount to a very large amount, you may encounter operations that suddenly take a bit longer than other operations because you have to do that copy step. One way to avoid that is just to initialize your array list with a size that's reasonably large enough such that you don't have to expand all that often. And ideally, you know something about your incoming dataset that you can make a reasonable approximation for how big the array list needs to be. Of course, you can't make it too big. If you make it too big, you end up wasting a lot of space with all those empty elements that are not filled. How about the append front operation? If I try to add to an index, something like index of 0, which inserts the element at index 0 and then shifts all the remaining elements over, that is going to be O of n. This is the equivalent of going to a apartment building and knocking on the first door you see and asking that person to move over one, and then everybody else has to consequentially move over one apartment. Appending to the front is something you can do, but it's also quite costly because you do have to move every single element down one index. The same thing behaves with inserting in the middle. If I try to inject an element into the middle of the array, it still involves shifting all the remaining elements up to the end of the array over by one index. That's still going to be O of n because in the worst case, I still have to move all those items. And the cost of moving all the elements over by one index is going to scale up linearly with the amount of items inside. Very similarly, removing is going to do the same thing. The remove method for the array list is going to take an element, remove it, and then shift all the successor elements over to the left by one, such that that gap becomes filled. Just like the insertion operation, you do have to move all those successive elements over by one index closer to the front, so that's going to be an O of n operation. With that in mind, we're going to see that some operations can end up being quite costly. It may be simple to think about adding or removing items inside the array list, but it itself is actually an O of n operation because of all that extra element shifting around we have to do. One of the readings I'm going to have you do this week is this bigocheatsheet.com. Big O Cheat Sheet is this website that has a table of several common operations and their Big O compared against several common data structures. You're going to see array on there, you're going to see list on there, you're going to see things like hash map and tree on there. Big O Cheat Sheet is a great reference, especially if you're memorizing some Big O runtime performance costs for algorithms, interviews, and the nature. What I would recommend instead, though, is just, well, have a good understanding of how the data structures work. If you understand how the array list needs to shift elements around in order to do expansion or removal, then you can also intuitively understand that, hey, removing from the middle or adding to the end may sometimes be O of n. I'll let you check out Big O Cheat Sheet on your own. Now I'd like to talk about how interfaces can abstract away runtime cost. Java interfaces like collection were designed so that runtime and storage costs for collection operations are abstracted away. Calling the add method, which looks relatively simple, can be computationally difficult because for something like an array list, we have to perform an insertion and then the migration of all the elements over by one index. Regardless of the backing structure though, the backing structure for the collection that is, if it's array-like or list-like or set-like, the Java interface is going to guarantee that those methods are always available. If the array list, the linked list, the set, they all fulfill the collection interface, then they're obligated to have certain methods, like the add method, which adds items, the contains method, which determines if an item is inside the list, and the remove method, which takes an item outside of the collection. So with that in mind, I'd like to pose to you this question for critical analysis. Are interfaces designed without considering runtime cost a good design? In other words, is it okay for a concrete class to fulfill an interface that it cannot fulfill efficiently? Let's think about some examples. With the array list, the add method and the contains method would both be linear time, including the remove method. An array list is a collection, therefore it's obligated to have these methods. And these one-line methods may look simple to call, but they're going to have this underlying runtime cost. Now let's consider a different structure, the linked list that we're going to learn about in a couple of weeks. The linked list is also a collection, but what I'm going to tell you is that add and remove may actually be O of 1 operations. Contains is actually still going to be O of n. However, from the perspective of a client of a collection, the add and remove method calls look identical, and yet they may still have different runtime costs. So do you think it was a good idea for the Java engineers to come up with this kind of catch-all interface for collections, even though the underlying runtime cost may be different for those collection operations? I'd like you to take a moment to think about this. Go ahead and pause the video, take a quick second, and pick a side. There's no right or wrong answer here, but I want you to consider one of the perspectives that we can take on this, either yes or no, and the argument for that side. Okay, hopefully you've taken a moment to think about it. If you haven't, please do pause the video and think about it. But otherwise, let's move on. So there's two ways we can go about thinking about it. Either yes, that we should expect as developers a consistent and predictable interface for all similar objects like collections, and the choice to use an inefficient concrete structure that backs the collection is the developer's fault. The other perspective is that, well, developers should never have to fall into this trap to begin with. The availability of an inefficient concrete structure to fulfill an interface is a bad idea. If a more efficient structure is expected to be used, then that more efficient structure should expose a specific interface for what it's trying to accomplish. That more specific method calls that it can do efficiently, instead of the more expensive method calls that should be hidden away. Java's going to take the side of, let's have this collection interface, and we're not going to care who implements it, and whether or not the implementation is efficient. C++ is kind of like the flip side of that coin. It's going to very deliberately expose only certain operations that it believes is efficient for particular structures. And you as a developer should go pick a different structure if those operations that you desire are not available. One operation that is efficient for the ArrayList is retrieval, indexing, the get method. In Java, indexing on the ArrayList is O of 1. In C++, indexing on the ArrayList, or the vector as it is in C++, is also O of 1. What about for linked lists? We're going to learn about linked lists very soon. But what I'll tell you now is that linked list indexing is actually O of n. It requires us to traverse the entire list to reach the nth element. In Java, though, a linked list is a collection. Therefore, we get access to that indexing operation, that get method, despite the fact that it's going to be computationally inefficient. In C++ land, the list, which is the linked list, is not going to expose indexing for us. It's not going to offer the option of using bracket notation to retrieve an index within the linked list. Now we can write a for loop and walk all the elements of the list to go find the index we're looking for, but it's not going to be as simple as this one-line method call that Java is offering us. So on one hand, the C++ implementation forces us to think about the structure that we're using and prevents us from taking the easy way out and using this computationally costly method. On the flip side, the C++ implementation is less efficient, or less convenient for us. Sorry, it is equally efficient, it's less convenient. In Java, all we had to do is know that, hey, a linked list is a collection, a linked list has a get method. In C++, we discover that we don't have something like the get method, we have to do it ourselves by writing a loop. Throughout the course of your computer science studies, you're going to find this sort of pattern a lot, is how much do we protect the developer from their own mistakes? Even something as simple as type checking, which is something that Java offers us, but maybe not as strictly available in a language like C, that is one way we try to save the developer from making certain mistakes. On the flip side, we may choose to trust the developer, and trust the developer with making the hard decisions and writing the code that is performant and works well without trying to introduce barriers. The typing flexibility of C and C++ is kind of like that. We can access raw pointer numbers. We can change their types on the fly, and the compiler is not going to complain. This pattern of developer trust and developer safety is one that we're going to see throughout this course and throughout the rest of your computer science career. So it's something you should keep in mind. What about memory management? We've talked a lot about runtime cost, but what about the practical internal memory management operations that have to happen when we find space to allocate a new array or a new object? Big O often does not consider these things. However, under the hood, there is a cost to find and allocate space inside the heap, this pool of memory where all objects live. Whenever we allocate space for a new array list, or perhaps expand a new array list, we have to scan the heap for a large contiguous space to fit that new array list. Scanning the heap itself does take time. Other structures are going to handle this differently. The linked list, for example, is going to distribute the elements across different regions of memory. This may be easier to manage on the heap side, because the heap doesn't have to go out and find a very large contiguous block, it only has to find a relatively small block and fit that new element inside. Some other things to consider: the cost of cache misses. Caching is something that you'll learn more about in an architecture class, but the short summary is that your processor caches a lot of the memory lookups that are typically going to require going all the way down to main memory. For common memory lookups at particular addresses, the CPU is automatically going to save a large block of memory that's read into the cache, such that later when it needs to access addresses within the cache, it can do so much faster than having to go all the way back to main memory. Computers are going to try and automatically store recently used and predictably used memory in faster cache storage, and some structures are better oriented for cache locality. The array, for example, is very good at caching. Because all the elements are stored contiguously, the CPU can read large chunks of memory at once and store it all in the cache. That way, when we're looping through the array or doing indexing, chances are a large portion of the array is already living inside cache, and it doesn't have to go read later in main memory. For other structures like trees and linked lists, we're going to find that the elements themselves are stored all across the heap, and it's much harder for the computer to decide to read a large piece of memory into the cache and find the elements that we're looking for inside the cache. I've got that written down here. ArrayList has the advantage in that its references are contiguous and more cache friendly. Several references can be loaded into the cache at once, whereas other structures are less cache friendly because they store data separately. Most of the time, we can ignore these practical memory management costs, but they can have real performance effects. In terms of high performance computing, you do really have to seriously think about cache locality and whether or not your processor is doing more work than it has to. Even though we can't quite encompass this cost inside Big O and Runtime, it is something we do have to pay attention to. And one of the readings that you'll be doing next week is going to compare the memory performance of the array list versus the linked list and examine how their impact on memory as well as their read-write performance can be based on the structures themselves. Okay, that's all I've got for today. As an exercise, I recommend you download these class notes and try to walk through all those sample algorithms and decide for yourself how to compute the Big O for each of those algorithms, and then check your answers against the notes you see in this lecture. We're going to be seeing a lot more of Big O in future lectures, so I hope that you become familiar with these relatively simple 3 rules that are provided to you. Have a data structure that is roughly of size n, count the number of steps relative to n, and then drop constants and constant multipliers. These 3 rules are pretty easy to remember, and it's something that you can hold on to for the rest of your computer science career. Thanks for listening, and I'll catch you next time.